What should technology be used for? As a society, we are faced with revolutionary technology, which, like all technologies, can be used for good or for bad. And we need to decide which technology we have to regulate and which technology we want to promote. To me, the answer to this question, what should technology be used for, was crystal clear when I was 18 and I had to decide what to study in college. Technology should be used to make robots. The first Iron Man movie had just come out, and I wanted to be the next Tony Stark. So I decided to study electrical engineering at Polytechnic of Turin. Of course, I immediately found out that I was not going to be the next Tony Stark. But I was still pretty decent at designing electrical circuits that could interface the physical world, which is mostly analog, with the digital world, which is what computer technology is based on. And so I ended up doing a PhD in microelectronics. Ultimately, I did not become Iron Man, but I found my passion, developing a brain-computer interface to treat incurable blindness. We call this technology the artificial retina. But before I talk to you about the artificial retina, let me tell you how you can even talk to the brain. It turns out that the neurons inside the brain communicate with each other using electrical signals. And thanks to more than 3 centuries of research, we know very well how these signals originate and propagate through the body. We also know how we can manipulate them. To make a very long story short, if you take a tiny electrode and you place it close enough to a neuron, it can listen to these electrical signals, and you can convert them into digital signals to be understood by a computer using the kind of circuits I was developing during my PhD. You can also go the other way around and use other kind of circuits to pass a tiny pulse of electrical current through these electrodes and talk to a neuron. If you now start doing this over thousands of electrodes, you can start talking with a small population of neurons and achieve incredible results. You can understand what the brain is telling you, and you can tell the brain what to do. Now, let's go back to our problem. Losing vision can be devastating for patients, disconnecting them from their surroundings. It is also an enormous economic burden to society. Diseases like macular degeneration and retinitis pigmentosa cause blindness by damaging the retina. The retina is the thin layer of neural tissue that sits at the back of your eye and is responsible for converting the incoming light into an electrical signal that the brain can understand. Now, due to these diseases, the retina is no longer able to talk to the brain, and the patient goes profoundly blind. A device that could talk to the nervous system would be a perfect solution to this problem. The idea behind an artificial retina is to electrically stimulate the retina to generate an artificial neural code to be sent to the brain and restore vision. But here is the challenge. For this to work well, the artificial neural code that we generate must resemble as much as possible the natural neural code, which is the combination of signals that a healthy retina would send to the brain when it's presented with an image. So the good news is that scientists have been studying the retina for decades, and we know very well how it works. In other words, we know what's the natural neural code for any given image. The bad news is that we don't yet have the technology needed to reproduce this natural neural code artificially with high resolution. But wouldn't it be great if we did? Science is giving us the answer to the problem. All we need to do is build the technology needed and make it available to humans. This is definitely something technology should be used for. But why is this hard? As usual, there is more to the story, and it turns out that the retina is a quite complex layer structure with many different neuron types performing all sorts of different functionalities. And reproducing this functionality precisely is just not easy. A very powerful example of this complexity is that of on-type and off-type neurons. An on-type neuron sends a signal to the brain when the light goes up. An off-type neuron sends a signal when the light goes down. And although all these neurons are intertwined inside the neural tissue, a healthy retina can orchestrate each neuron type very precisely. When we stimulate the retina artificially, we must respect the same specificity. Otherwise, if we were to stimulate neighboring on-type and off-type neurons at the same time, Effectively, we will be telling the brain that in a certain region, the light went both up and down at the same time, which is a very confusing signal. So what we need is an orchestra director. Indeed, I like to think about this very much as an orchestra because it fits very well our situation. Think of each neuron as a musician and each different neuron type as a different instrument. As a director, you could tell all the instruments to play the same note at the same time, and sound will come out, but it won't be music. Now, if you want to create music, you need to be able to tell each instrument which note to play and when. In the same way, if you want to create vision, you need to be able to stimulate each neuron individually. Technology is our orchestra director. Electronics to tell the retina which note to play and when. So, over the past 10 years, with my team at Delft University of Technology, we have been trying to develop this little orchestra of ours. And we are getting very close to having the first device ready for implantation. The device is just a few millimeters square, but it packs a lot of electronics inside. It sits at the back of the eye, close to the retina. It has more than 1,000 electrodes, each thinner than a strand of hair, and a very powerful chip to control all the electrodes. It communicates wirelessly with a computer and a camera that are mounted in your glasses, and it works in 2 steps. At the beginning, during calibration, the device learns which type of neurons and which neurons are near the electrodes, and also it learns how to stimulate each neuron individually. What we are doing here is learning how to tell the retina to play all the different notes that we need. After that, during runtime, we can use what we learn, take an image with a camera, and select how much current to pass on each electrode to activate the specific neurons that will recreate the natural neural code with high fidelity, so that we can send the correct information to the brain and make the patient see again. So where are we at this moment? Our neuroscientist collaborators at Stanford University can already do this, but using a room full of equipment. To fit this inside the human eye, we need to reduce the size of this experimental setup by 10 to the power of 9. In other words, we need to make this picture 1 billion times smaller. And this is where the power of microelectronics come into place. The ability to pack all this functionality inside a very tiny chip that fits on the tip of your finger. So, what does it mean for the future if we succeed? High-fidelity artificial vision could improve the quality of life of millions of people worldwide. If we are able to reproduce the natural neural code in the retina, we could create a representation of the outside world that matches reality. But we need to be very careful, because someone could also misuse this technology to create a fake representation of the outside world that would make deepfakes look like a joke in comparison. Like that episode of Black Mirror, where the military implanted chips in the soldiers so that they would see the enemies as monsters and feel no compassion when killing them. Again, what should technology be used for? Myself, I'm an optimistic, and I think that technology should be used and will be used for good. Beyond vision restoration, if we are able to reproduce the natural neural code in the brain, we could help other patients suffering from all sorts of neurological disorders, like Parkinson's disease, epilepsy, dementia, and so on. And thankfully, there is many other crazy people like me out there that are trying to make this technology a reality. So, what have I learned since I wanted to become Iron Man? If you consider how we moved from the radio to the TV to the smartphone, technology has been getting closer and closer to us. With brain-computer interfaces, technology would be so close to our consciousness that it would be very hard to differentiate us from robots. Probably, artificial intelligence is the biggest technological development in our lifetime. Brain-computer interfaces will be even bigger than artificial intelligence because they will change what it means to be humans. With that in mind, let me ask you one last question before I leave you tonight. How should we use our most transformative technology? I don't have the answer, but the question is very much on the table. And we should all reflect on this, because this technology belongs to all of us. We cannot become Iron Man. Believe me, I tried. But we can be active in the choices that affect our lives. And the more we are aware of the use we want to make of technology, the more we can influence its future developments and make sure that it has a positive impact on our lives. Thank you very much.